So we've now defined what a singular point is. If F is not analytic, in other words, is not holomorphic at a point S, but there exists an open region R surrounding S, where f of z is analytic. Then S is called a singularity. This is just a word. So basically it means where the denominator is 0. Denominator is 0. So you have a certain region R, and you have this point Z0 where, or let's call it S. It's changing the names all the time here. For this theorem, we're calling it S. So Z could be some other point, and the radius, let's say, is R there. Another way to express the radius is Z minus S. So we can say Z minus S, the absolute value, is between 0 and R. This region R is called a punctured disk. Punctured disk. It's like they're one point removed from it. It's a holomorphic region, but one point has been taken out. Okay, I think that's very simple to understand. That's just a note on the word singularity. So some important series that we have come across. Now that you are in third year, you should be committing some of these things to memory, so you can remember them, like e to the z. That's z to the k over k factorial. K equals to 0 up to infinity. Cos z. Well, let's take cos z first, cos z, because cos z is more interesting. It's z to the 2k over 2k factorial from k equals to 0 to infinity. Cos z is about the same thing, except there's a minus 1 to the k here. Z to the 2k over 2k factorial. In other words, here the signs alternate, plus, minus, plus, minus, plus, minus. Whereas there the sign that is plus all the time. Right, so these are some famous ones. Sine also can be written as a 2k plus 1 over 2k plus 1 factorial. Minus 1 to the k. Sinh will have the same thing here over 2k plus 1 over 2k plus 1. And then you can write tan, hyperbolic tan, and so on. But now, we're going to focus on the geometric series from high school. This is very important to understand. So if you take 1 plus z squared plus z cubed up to infinity, the formula is a over 1 minus r, so it's 1 over 1 minus z. It converges in the circle absolute z less than 1. The radius has to be less than 1. And so inside that circle, geometric series will converge. You remember this? In other words, I can say the sum of Or I can write 1 over 1 minus z as sigma z to the k equals 0 to infinity, provided that mod z is less than 1. If I switch z minus z, because I can get another formula. If I tweak this, let's say I make z into minus z, then I can get 1 over 1 plus z. And here it'll be minus 1 to the k, z to the k. That means an alternating geometric series, 1 minus z plus z squared minus z cubed, etc., will be 1 over 1 plus z. We know that anyway. The ratio now will be minus z. So a over 1 minus r will be a over 1 minus minus z, 1 plus z. But I just tweak this formula, replacing z by minus z throughout. I get the desired result. Something else I can get here is I can integrate this. Integrate this last result. Integral of 1 over 1 plus z dz. Oh, let's go with the dummy here. 1 plus w dw. Suppose I want to go from 0 to z. Do I know the integral? What is the integral of 1 over 1 plus w? Anyway, I am integrating both sides, so let me integrate this side here. So you can see this will be integral of minus 1 to the k, z to the power k plus 1 over k plus 1 factorial. K plus 1 itself, not factorial yet. K equals 2, 0 to infinity. If I integrate z to the k, is z to the k plus 1 over k plus 1. That's a normal integral from first year. There are no factorials involved here. What I just want to show is that we know this is a log integral. So this is actually log of 1 plus w from 0 to z is minus 1 to the k, z to the k plus 1, k plus 1. In other words, this is log of 1 plus z. If I replace w by z, carry out this integration, but substituting z here first, 1 plus z. Then I substitute 0, log of 1 is 0. So I can expand this. This will become like, so when k is 0, infinity. When k is 0, this will be z minus z squared over 2 plus z cubed over 3 minus z to the 4th over 4 plus blah, 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 blah. So that is a series for log of 1 plus z. We don't talk about log of z itself because z at 0, log of 0 is not defined. Therefore, we shift the log function by 1 unit to talk of log of 1 plus z. Oh, also recall more facts. You see, you put all these things together, they're quite interesting. Log of 1 plus z. It's a complex number, say, so it's ln of 1 plus z plus I argument of 1 plus z. Sorry, 1 plus z. But this doesn't tell us much at this stage, so I'm just putting that as an interesting aside. Log of 1 plus z is the ln of 1 plus z. It means you have to find the radius here to z plus 1. That's 1 plus x plus iy. We'll have to find the square root of x plus 1 squared plus y squared. Right, so that's that. Okay, let's take a couple of examples now. The last fact wasn't useful, but let's keep it now memory. Example, let's say expand. Let me deal with the example in the book this time, because when you read it, it can be a bit confusing. There are 3 or 4 different scenarios that are dealt with one at a time. I'll show you the differences between each one. So expand f of z equal to z over z squared minus 5z plus 6 about z naught equals to naught. In z equals to, let's say, 10. Okay, so I want to expand a function of this type about the point z naught equals to naught. I want to find the Taylor series expansion of this basically. So, well, I can do it by differentiating it many times and stuff, but there's a straightforward approach. We can write this as z over, let's factorize this, z minus 3 into z minus 2. And if I do the partial fractions, it'll be 3 over z minus 3 minus 2 over z minus 2. In retrospect, this wasn't a very good choice of numbers. I should have had z squared minus 6x plus 8. Then you have the same numbers. 3 is there, 3 is there. Not a good choice of numbers. Anyway, so that's where it goes now. So I want to expand this about z equals to naught. In other words, I want something with z squared, z cubed, z to the fourth, etc. How can I expand it in that manner? So consider, let's take the first one. You don't have to break it up in future, but let's do it step by step. 3 over z minus 3. Note, we have a formula for this. We have a formula for 1 over 1 minus z. It's sigma z to the k, right? We know that. That's the geometric series formula. I just put that up earlier on also. X z, 1 plus z squared plus z cubed, etc. boils down to 1 over 1 minus z. Now I need to massage this guy to look like that. I need to massage him to look like that. So I can then get z to the power k. But the thing is, I must have something minus z. So the first thing I need to do here is divide the numerator. I want to get a 1 also on top. Divide the numerator and denominator by 3. So I'll get a 1 on top. Z over 3 minus 1. So far, I've got the 1 on the top. There's a 1 here. There's a 1. Now I want to have it the other way around. I don't want to have it as z minus 1. I want it as 1 minus z. So then I have to massage it again and put this as minus 1 over 1 minus z over 3. Things have switched around. And this will be minus sigma z over 3 to the power k. K equals to naught to infinity, provided that z over 3 is less than 1. In other words, z is less than 3. If that is valid inside z less than 3, within the circle z equals to 3. In other words, I pick this part. This part is sorted out. See, I'm going to make it good by that. 1 over 1 minus 3. There's a 3 here. The first part of the game is to divide by 3 to make it a 1. But you have to do it in numerator and denominator. When I do it, I get 3 over 3 is 1, z over 3 is 0 over 3, minus 3 over 3 is 1. Now, that thing is going to switch around, 1 minus it. So I'm going to adjust that. The trick to adjust it is to make it a minus there and 1 minus. Now it looks exactly like that. Except that when you go to z, you go to 0 over 3. So that's fine. So the formula will become, it's a negative here, z over 3 to the power k. That's the formula. This formula will have z1 plus z squared plus z cubed. There will be something at the bottom, like some power, 3 to the power 1, 3 to the power 2, 3 to the power 3. That's fine. Now, let's take the other guy. The same thing happens there. We take, so I finish with this guy here, right? I'm taking this guy. Let's take 2 over z minus 2. Again, I want to massage him in the same shape. First thing is divided by 2, so it will become 1 over z over 2 minus 1. Then switch things around, minus 1 over 1 minus z over 2. Then it's minus sigma z over 2 to the power k. K equals to 0 to infinity. This is valid. This is the important part. Z over 2 less than 1. In other words, the radius is 2. Multiply both sides by 2. So this is valid inside 2. And remember, I said the big circle is 10. So all these things are in the game. You don't have to worry about the big circle here. In any case, the point z equals to 2, z equals to 0. Note, z equals to 0 is inside both circles. Z equals to 3 and z 2. So in conclusion, I can say f of z is the first guy, this one here, this minus this, green minus the yellow, that minus that, and that's the series that we require. It will be negative z over 3 power k, k equals to 0 to infinity. Minus times minus becomes a plus. You see, this is a minus here. Minus, that minus times the yellow thing is minus, becomes a plus. And then the yellow stuff I write down. Z over 2 power k, k equals to 0 to infinity. You want to expand this. So you can write this as, I can expand this. When k is 0, it will be 1/3. Plus, when k is 1, it will be z. I mean, it'll be, sorry, when k is 0, this is a 1. When k is 1, this will be z over 3. When k is 2, it will be z squared over 3 squared. Plus, blah, blah, blah. Plus, this one here, likewise. When k is 0, this is a 1. Plus, when k is 1, it will be z squared, z over 2. Plus, z squared over 4. Plus, z cubed over 2 to the power 3 is 8, etc. Then you can combine these two. The ones will cancel off actually. You see, the ones will cancel off, so you'll have z over 2 minus z over 3 plus z squared over 4 minus z squared over 9 plus blah, 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 blah. So that is the sequence. Where's the cube here? What do we have 4 here? Z squared over 4. Oh. That's a square term. The next one will be a cubic term, and the fourth order term, and so on and so on. So that is a series. That is a series representing that function I gave you at the beginning. Z over z squared minus 5z plus 6. Within that circle, of course. So I'm now going to change the picture slightly. I'm going to change the, why is a mixture here? Okay, z equals to 4. Because if you look above, your partial fractions has got this minus that. Yeah, so that minus there, subtract this down here. So now, so in this problem here, you've got two things. You've got the radius 2 and the radius 3. So what if you have a point outside these two radii? You see, z equals to naught. Let's just see what I'm saying. In this problem here, you have two circles, z less than 3, z less than 2. Well, lousy circles. The fix is very easy. You just have to redraw this axis. Right, so that's 3 and 2. So we dealt with z naught. The point is right in the middle of both these guys. That's quite a harmless, the least harmful situation. What happens now if I want the sequence to converge at x equal to 4? Now I need the radius to be outside. So these ones had z over 3 less than 1. Outside it would be z over 3, this is inside. Outside, I need to have z over 3 more than 1. In other words, z more than 3. I will now need to massage in such a way that I have that happen. Okay, let me take an example. And of course, you may even be wondering, what happens if you have a point here in between the two guys, two circles? That would be the third configuration. First, I took one in between both of them. Now I'm taking a case where the point z is outside both of them. Then I'll take a z that's in between both of them. Those are the three types that you can get. So this second problem is like this. Example, let's do example 32. Well, I'm doing the same example in the book. Expand f of z, the same one, z over z squared minus 5z plus 6, that converges for z equals to 4. I didn't say mod z equals 4. Mod z equals 4 is a set. Z equals 4 is just a point. 4 plus 0 I. Okay, solution. Again, we know that f of z is 3 over z minus 3 minus 2 over z minus 2. So as I said, now we need mod z to be more than 3 and mod z to be more than 2. If it's more than 3, then it's obviously more than 2. So here comes the sinister maneuver. If you take 3 over z minus 3, divide the top and bottom by z. So you will have 3 over z all upon 1 minus 3 over z. What is the motive behind that? So I don't want z over 3, I want 3 over z. So that, see now I have massaged it to get 3 over z. If I have z over 3, then it will be z less than 3. Now it will be 3 over z less than 1, 3 less than z, or z more than 3. That's why this trick is done. There's only two tricks. One, you divide by the number to get a 1 on top. The other one, you divide by z. So then this becomes 3 over z, and this now becomes sigma 3 over z, not z over 3, the power k, k equals to 0 up to infinity, 4, 3 over z less than 1, must converge, so the radius has to be less than 1, but this boils down to saying 3 less than z, or z more than 3, as required. That's what we want, as required. So this is the formula now, if you want it to be z more than 3. If you're confused, just ask me to repeat. If you want a re-explanation, just tell me. Now I'm going to take 2 over z minus 3. Again, I want this to be outside 2. So I want the same thing again. Okay? As you can see, now if you take the third case where the point lies between the two circles, then one will have to be like example 1, and one will have to be like example 2. I must have one to be less than 3, the other one to be more than 2. That will be the difference in the third example. But this one follows the same path. Divide the top and bottom by z, you'll get 2 over z all upon 1 minus 3. Where's this 3 from? That's a 2, right? 2 over z. So that is 2 over z sigma 2 over z to the power k equals to 0 to infinity. And this is valid for 2 over z less than 1. That is z more than 2. So to conclude this part here, you can say f of z, let me just write this last sentence, will be 3 over z sigma 3 over z power k. K is 0 to infinity. Minus. There's no minus sign that appeared here in the calculations. So it's 2 over z sigma 2 over z power k. K equals to 0 to infinity. That is the sequence. And that will be valid for z more than 3. Z more than 3 covers both guys. You can't say z more than 2, because one of them is more than 3 also. Well, actually, you can say z more than 2, because z more than 2 covers both. What am I saying? Z more than 2. No, you have to say 3. Because if it's more than 3, it doesn't necessarily mean more than 2. But now it will be. If it's more than 3, it will necessarily be more than 2, but not the other way around. All right, we stop here. In the next lecture, I'll deal with the third case.